So today we talk about nuclear chemistry. What's going on in the nucleus? Because Dalton was wrong. He's been wrong about a couple of things. He said atoms of the same element are identical. They're not. I can have different weights of the same kind of atoms. They can weigh different amounts, otherwise they'll be the same. Those are isotopes, which was what your nuts and bolts were. The three kinds of nuts were three isotopes of nutium. The two kinds of bolts were two isotopes of boltium. So now we're going to talk about another way he's there, and to do that, we actually have to talk about, like, why does the atom stay together? What's going on? And that was today's Bellward question. Today's Bellward question is, the nucleus should fly apart. If you think about the two questions. What kind of parts do you have in the nucleus? You've got positive and neutral. If I put neutrals together, what happens? Nothing, right? If I put a positive next to a neutral, what happens? Nothing. But if I put a positive next to a positive, they repel. So in that nucleus, I've got positive pieces. Remember how tiny the nucleus was compared to the whole atom? So I've taken those positive pieces and put them really close together. How come they stay together in the nucleus? I got something pushing them apart, but nothing holding them together. There must be a force besides charge. Charge does not explain why there's a nucleus. I should not be able to put two protons next to each other. But instead, inside that huge atom, I cram the two protons in the tiniest space. That would be, the two protons can be anywhere in a baseball field if they're anywhere in the atom. But no. The whole baseball field, those two protons have to go inside the baseball. Make sense? And they don't want to get that close together. They're going to push each other apart. Well, there's some other forces. There's two other forces that you don't encounter anyplace else. And they are given names like, well, these are the actual names. The first one is called the strong nuclear force. Which only leaves us one possible name for the other one. But if it's not the strong nuclear force, it must be the weak nuclear force. Now, why don't we see these, why don't we experience them anyplace else? Well, the strong nuclear force is between protons and protons. It stops working if you get bigger than 10 to the minus 15th meters. If you get bigger than 10 to the minus 15th meters, the strong force doesn't reach that far. So it only, and that's about the size of a nucleus. The force doesn't reach out any further than that. That's why the nucleus is that small. Because it only reaches so far, so it's got to be held in that tiny space. And that's between protons. The weak nuclear force is actually what keeps the proton together. There are parts inside the proton called quarks. And the weak nuclear force keeps those together. So it holds the proton to itself. Okay? And that you have to get to 10 to the minus 18th meters before you see that. So little tiny numbers. Okay? Strong nuclear force, weak nuclear force, they're both attractive, but they both have limited reach. So they only work inside the protons and neutrons and inside the nucleus altogether. Okay? So we got a tug of war between the positives pushing out and the nuclear forces pulling in. And if things get off kilter, the positives can win and that nucleus can fall apart. Okay? They noticed something, though. If you take and add up the mass of the proton, the mass of the neutron, and the mass of the electron, you get a number that's bigger than the atom. Sorry. I closed it too early. I got to get back. This just sounds strange. So this is what we're used to doing. If I add up how heavy all the parts are, that's how heavy the thing's going to be. It doesn't work with atoms. Okay? If you take the numbers, and actually just take the numbers, and you take the mass, oops, where'd it go? That's not where it was when I changed pages. I love how it does that to me. Okay, so for a helium 4-2 helium, that would be 2 protons, the 2 protons would weigh that. 2 neutrons, the 2 neutrons weigh just a tiny bit more. They actually looked up the numbers. And the 2 electrons, like that. So that adds up to 4.032997 AMUs. But if you weigh a helium 4, it only weighs 4.00206. It weighs that much less. Okay? Which is enough to be measurable. They can notice that. If you notice that, if it weighs less, that means Dalton was wrong again. But he was wrong not about his theory. He was wrong about his law. Mass got destroyed. All the protons, neutrons, electrons turned into an atom, it weighs less. Somehow mass got destroyed in that process. 0.03038 AMUs for every helium atom. That 0.03 AMUs, that's the mass defect. It's called mass defect because your mass is defective. Where'd it go? So I'd say this because I find it over and over again, people still saying that laws are more certain than theories. But they're not. As soon as they saw this, they knew that Dalton's law of conservation of mass was wrong. And they had to come up with a new law that explained what was happening. So laws and theories are equally certain. They're just answering different questions. And when you find something that the law doesn't describe, you need a new law. So where did that mass go? It's got some missing mass. Where did it go? Well, first thing we find out is the law of conservation of mass does not work in nuclear changes. Because they added up the numbers that go into making a helium atom, and the numbers weighed more than the helium atom. I mean, it sounds like it's strange that if you add up the parts, it adds up to the whole. That could be a job. My friend graduated with his engineering degree, went to work for Boeing. And his job the first 6 months he was there was to figure out how heavy the 747 was going, the 747 they're building was going to be. They'd changed a whole bunch of parts. They wanted to know how heavy the plane was going to be when they built it. So how do you find out how heavy the plane's going to be when you build it? Well, you figure out how heavy every single piece will be. And then you add them all up. Okay? And it worked. It doesn't work for atoms, though. You add up all the pieces, it weighs less when you're done. Where did the missing mass go? Well, there's a bright man who figured out what was happening. And he could write it in just a short little statement. E equals mc squared. Einstein's theory of relativity explains what happened. What do you think E stands for? E is energy. M, the equal sign, the word is. This says energy is mass times a conversion factor. And the conversion factor is the speed of light, which is 3 times 10 to the 8th meters per second. So that mass that got destroyed turned into energy. That Einstein was saying mass is energy, and energy is mass. So that little bit of mass you destroy creates a whole bunch of energy, because that C, you have to square that. So I got to square that 3 times 10 to the 8th. That's 9 times 10 to the 16th. That's a big number. So if you multiply a little tiny mass destroyed by a really big number, you get a lot of energy. A little bit of destroyed mass can make a huge amount of energy. I mean, this simple equation explains so many things. E equals mc squared. It explains why nothing goes faster than the speed of light. Because if you're going faster, you have more energy. Everybody agree? That a slow-moving car, and a car on the freeway running into something, the car on the freeway has more energy. The faster you go, the more energy you have. But this says the more energy you have, the heavier you are. Energy is mass. So as you start getting close to the speed of light, you start getting noticeably heavier, which means the heavier you get, the harder it is to speed you up. So I'm going so fast, I put in some energy to speed up. If I want to speed up 10 miles an hour, if I put in energy to go up 10 miles an hour, the next 10 miles an hour is going to take more energy because I'm going to be heavier. And the next 10 miles an hour is going to take even more energy because I'm even heavier. And eventually, as you get close to the speed of light, you end up with an infinite mass that you would have to push with an infinite force to go any faster. And that's why the speed of light's the speed limit, because we can't push with infinite force. Okay? Because energy is mass. You don't see it until you get going to the speed of light, though. Okay, so that little bit of missing mass, that little bit of m, multiplied by c squared is 9 times 10 to the 16th, is going to give you a huge number for energy. And that energy's got to come out of that atom. It'll come out as either light we can see or particles that go flying. And that is radioactivity. When that mass gets destroyed, it's got to get rid of the energy. The energy's got to fly out of that atom somehow. It will come out as a particle or as just energy in terms of light. So that's radioactivity, that's radiation. And if something is radioactive, it's radioactive. the nature of the atom itself that makes it radioactive. Spontaneously means you don't have to do anything for it to happen. You sit there. Now, this process is unaffected by changes in temperature, changes in concentration. Normally, when I change the temperature, reactions change speed. Nuclear changes don't change at all. If I make it more concentrated, usually reactions get more violent. It doesn't change. It doesn't matter if you react it with something. Radiation comes from the nature of the atom itself, not what it's combined with, not what it's hooked to. That atom is radioactive. One atom at a time, you decide whether it's radioactive. So that they want to separate the radioactive uranium from the non-radioactive uranium, they can't use chemistry. They can't use any chemicals to separate them, which was what Marie Curie had a problem with. Was she was trying to isolate something that the radium, it didn't matter what she did to it, it always stayed radioactive. And she found the only way she could get more radioactive would be to concentrate it down, to take the same stuff and put it into a smaller space. So the speed is only affected by how much you have. So if you have lots of the stuff, the reaction goes faster. If you have a little bit of the stuff, the reaction goes slower. And that's simply because it's random. It's just randomness that makes that happen. Because if you start off with, say, I'm going to pick an easy number, 32 people, and you have them all flip a coin. After that first coin flip, you can expect 16 people to leave. Right? 50-50 chance, 32 people. So in the first coin flip, you lose 16 people. Then you do another coin flip with the 16 that are left, because there's going to be the things that didn't change are still radioactive. Another flip, this time only 8 are going to change, because you've only got 16 left. So it seems to go slower over time because you got fewer and fewer atoms that are falling apart. The reason lots gives you lots of radiation is because there's lots of atoms that could fall apart. Each individual atom has a chance of falling apart, and it's independent. Okay, there are 3 kind of particles we need to talk about, and one of them we've already talked about. Spent a whole bunch of time in the first half of this chapter talking about alpha particles. And an alpha particle is a helium-4 nucleus. So it says it's a helium-4 nucleus. So it says it's helium. It says it has a mass number of 4, and helium's atomic number is 2. So that's an alpha particle. An alpha particle is a helium nucleus. Now, so when you take that helium-filled balloon, what you really have is a balloon full of alpha particles that have picked up some electrons. All the helium that you ever used in your life came from radioactive decay inside the Earth. Because once helium gets to the surface, if you got a helium balloon and you pop it, that helium rises without the balloon. And when does it stop rising? When it's left Earth. It goes out into space, travels off into space, and it goes off the Earth forever. So every bit of helium that you use is coming from underground. They find it in the same place they find natural gas, where there's a big salt layer that'll trap the gases. Well, it traps natural gas, and if there happens to be a radioactive pocket beneath that, it catches the helium too. So in Texas, there's there's an area where the wells have an especially high content of helium with their natural gas. So they separate. It's worth the money to separate it out. But what you're using every time you pop a balloon, you are throwing away 3 billion-year-old alpha particles. It took 4.5 billion years to build all those up. Helium's going to get expensive in your lifetime because we're using it all up for party balloons. And we need it for the fastest computers we make now. We need liquid helium. So we need the helium. Helium's going to get really expensive. But it's all alpha particles. Radioactive decay underground. And we know that's what's keeping the inside of the Earth warm. The inside of the Earth is melted because there's still radioactivity down there giving off energy. This is how we describe the alpha decay of polonium-210. Polonium-210, there's an arrow saying it's changing. So the stuff on the left-hand side of the arrow is what you start with. Stuff on the right-hand side of the arrow is what you make. So remember, our helium nucleus is 2 protons, 2 neutrons, no electrons. That's how you get a helium-4. And we want just the nucleus, because it's got to come out of the other nucleus. But because of those pieces, it's got a positive charge, and it's the most massive particle. And that's what Rutherford knew about it when he was shooting them out. That's all he knew, was they were positive and pretty massive. That it would take something really massive to make those alpha particles turn. That's why he knew there was a nucleus. The few that turned told him how small it had to be. The nucleus was tiny. They talk about it taking a couple of years for Rutherford to go between experiments and publishing results. It was because he didn't believe the numbers. He couldn't believe anything was that dense. But it's the only way the numbers worked. Couldn't believe anything was that small, but it's the only way the numbers worked. Okay? Every time I do this, notice that I started off with the atomic number 210, and I ended up with the atomic number 206. Mass number. The top number is mass number. Because those mass numbers have to stay equal from one side to the other. So 210 equals 206 plus 4. And the bottom numbers, the 84, I made number 82 and 2 more. 82 and 2 is 84. The bottom numbers have to equal each other. The mass numbers have to equal each other. The atomic numbers have to equal each other. So every time you do an alpha decay, your atomic number is going to go down 2, because you got to make this, so the other one's got to go down 2. Since I'm going to make, I got to have 2 protons here, I have to lose 2 from my big atom. And I got to take 2 protons and 2 neutrons from my big atom. So the mass number is going to go down 4 every time. Because you're taking off 2 protons and 2 neutrons, and top number is protons plus neutrons. They call it the alpha particle because it was the first particle they found. And alpha is the first letter in the Greek alphabet. The second letter in the Greek alphabet is beta, because you can put stuff in alphabetical order. That's where it got its name, alphabetical. And beta is the second kind they found. And a beta is an electron that comes flying out of the nucleus. The kind of carbon they use for radioactive dating is carbon-14. Carbon-14 undergoes beta decay and turns into nitrogen-14. Excuse me. Anybody see a problem with this? How many electrons are in the nucleus? There aren't any electrons in the nucleus. If there's no electrons in the nucleus, how can the electron come flying out of the nucleus? Well, you'll notice that my number of protons changed. So I didn't just make a negative piece. I also made a positive piece. So what happened is a neutron gives up an electron and becomes a proton. Because if you're neutral, you got positive and negative pieces. Get rid of that negative piece, you're left positive. So it turns out the quarks that make up neutrons and protons are held together with that weak force. And occasionally that weak force isn't strong enough to hold them together. It's not strong enough to hold the neutron together. That's a strange thing to say, right? Not strong enough to hold the neutron together. So this is a beta particle. It doesn't have any protons or neutrons, so its top number is 0. And the negative one here is not the charge. The negative one here is so the math works out. 7 plus what gives you 6? Negative 1. So that's the symbol for a beta particle. You could also write it with the Greek letter beta. Same numbers. The beta became our B, in case you can't tell. And every time I do this, the atomic number is going to go up 1. Because if I make one of these, this number, the atomic number's got to be 1 bigger on the piece before it. And the mass number is unchanged. The element is changing. Dalton was wrong. Remember, he said elements don't change into elements? He was wrong. Elements do change into elements. Oh. Did we throw away the idea of atoms because they found out elements change into elements? No. So that's why I said theories get modified, they don't get thrown out. We got to explain the new stuff. Okay? And like I said, this is the same thing, all I did was that beta sign. Okay, the last kind of particle we're going to talk about coming out is a positron. What do you think the charge on a positron is? Positive. Okay, so it's a positive piece. Turns out it's the positive piece that's exactly the same size as the electron. It fits into a category of material we call antimatter. Positron is antimatter. There's 2 sets of rules for building a universe, where the only difference is the signs are changed. Positive and negative change signs. The one we live in we call matter. The one that works for us is called matter. The one that works the other way with the opposite sign is called antimatter. And if you put matter and antimatter together, annihilating, and all the mass gets turned into energy. It doesn't just lose a little bit of mass, the entire mass disappears. Black hole, no, black hole actually all the mass stays there. It's in the same spot. It just becomes more massive. So it pulls in more stuff because it's got more gravity. So it's so antimatter. You don't see positrons because they run into an electron before they see you and they get destroyed. Okay? You don't want to get hit by a positron because you got electrons in you. And when a positron hits an electron, you get energy. So let's look at these. This is going to do positron emission. And there's the positron over there on the end. See how it's different from the beta? The big difference is it's got a positive number on the bottom instead of a number. Okay? So what number is going to go on top? It's got to be 38, right? Because the numbers up top have to be the same. This one's 38. The other side's got to add up to 38. What plus 0 is 38? Okay? What's the bottom number going to be? What plus 1 equals 19? That's 18. And since it's number 18, that tells me it's argon. Pretty easy to work with these equations. Once you know what that piece is, all you have to do is say, I'm going to make that piece and what else? So a proton gives up a positron and becomes a neutron. Ooh, the proton changes into a neutron by giving up a positron. How do we know the proton changed? Because I went from 19 to 18. But I didn't change mass numbers, so that proton that disappeared had to become a neutron. So you can think of the positron as a neutron, or a proton losing its positive charge. A beta particle as a neutron losing its neutral charge. So every time we do this, the atomic number is going to go down by 1, and the mass number is going to be unchanged. So we got those three types of decay I need you to work with today. So you're going to be writing some of these equations. And you could also use the beta with a positive sign. This is equally acceptable. Oh, I never showed you what an alpha looked like, did I? Alpha. That's the Greek letter alpha. Looks like a fish. So identifying the missing particle. Well, I got potassium 42, and then I make a particle. What's the top number got to be? 42. What's the bottom number got to be? What minus 1 gives me 19? That would be 20. And then number 20 is calcium. There, that's it. Except I'm going to ask one more question. What kind of decay is this? What's that? What kind of piece is that? That's a beta. So it's beta decay. Ta-da. Don't make it any harder than that. Make the numbers work out. Hey, radium. This is what Marie Curie was looking at. Those were her rays from the movie. They were alpha particles. Yeah. So, what number goes on top? 222 plus 4 makes 226. Bottom number, what plus 2 equals 88? 86. And number 86 is coming off the wall. And number 86 is radon. And what kind of decay is it? That's an alpha particle, right? So it's alpha decay. Okay, pretty easy. Actually, there's one I want to do. Write the equation for the alpha decay of neodymium-144. I'm not asking you any new skills. You just got to remember where to put things in relationship to the arrow. Alpha decay of neodymium-144. So where does the neodymium-144 go? It's on the left-hand side, right? Correct? That's what I'm starting with. Where does the alpha go? It's on the right-hand side, right? And an alpha is for, no line, 42He plus 140, 58. 58 is cerium. Okay. Extra super tough? Okay, here we go.